Assalamualaikum and good day everyone. So we will discuss about week 7 syllabus, okay, which is magnetostatic field. Okay, so now is 27 of April 2021. Okay, the lecture is recorded from 2:11 a.m. okay, in the morning. Maybe you guys are sleeping right now. Okay, so today is Monday. Okay, so we will discuss about magnetostatic. Okay, magnetostatic. Okay, so this is the beginning chapter where we will start discussing about magnetostatic. Okay, no more about electrostatic, and later on we will combine them afterwards. Okay, so now is a starting for us to explore about the magnetic world. Okay, so just like electrostatic, okay, what we understand from the words magneto and static. Okay, so magnet mean we only discuss concerning magnetic field only. Okay, only. And for the static field, it means that is independent of time. Okay, so we will not include the element of time. Okay, and we only consider the usual coordinates. For example, if you have your h, okay, for Cartesians, okay, for Cartesian x, y, z. For the cylindrical, what is it? R, v, and z. For the spherical, r, v, and theta. Okay, so just like magnetic electrostatic field, they are quite similar, okay, in some ways, and only different in certain ways. Okay, so it's easy to make analogy. So for this magnetostatic field, okay, you can start reading from chapter 7. Okay, chapter 7, page number, oh, there is no page. Okay, 292 means this one is page 291. Okay, you can start to see from here to everything, and you can see it is interrelated. Okay, you can make analogy between the electric field and magnetic field. Okay, just for us to see, brush through first before we explore this lecture further. So you can see basic law. Okay, you see you have your F here for electric field, Q1 Q2 over 4 pi epsilon naught epsilon r square. So what is this? This is your beloved Coulomb's law. Okay, so and then you have dds equals to q enclosed. This is your Gauss law. Okay, so if this is your force, okay, this is your force, dB is what? dB is actually, B is actually magnetic field density. Okay, then H is what? Electric field and magnetic field intensity. Okay, so please forgive me if I mistaken in pronouncing or what typo. Okay, I think you guys understand due to the time. Okay, so the force law, we have F equals to Q over E, and here you have F equals to QU cross of B. So what is U? U is your moving charges. Okay, however, moving charges at a constant speed. Okay, so this is field intensity. Okay, flux density. So you have B here, D here. Relationship between fields, you have electric flux density and electric field intensity. This one is magnetic field density with magnetic field intensity. So this one potential, this is potential gradient. Okay, this one is the corresponding for the magnetic field. Energy density, Poisson equations. Okay, so let me go to the definition first. Okay, the definition phase. Okay, you know, maybe a bit boring. Sometimes I show the book because it is for the benefit that those who doesn't have the book, but I cannot show it, all the books, right? Otherwise our video, maybe I don't know how long I will need to record it. maybe I still not finish record. Okay, so this will be like your free mark later on. Okay, maybe if the question asks what is Biot-Savart, you should be able to explain. Okay, Biot-Savart law stated the differential magnetic field intensity, our DH, produced at a point P, okay, as shown in figure 7.1. Okay, here this is your DH, okay, means small differential of electromagnetic field intensity. Okay, by the differential equation IDL, if it's I the filament current, okay, filamentary current, and DL of course is the displacement, okay, differential displacement. So you can have dx, dy, dz for the Cartesian, and so on for the cylindrical and spherical. Okay, this one is you have learned already from previous chapter. I dl and the sine of the angle alpha between the element and the line joining P to the element, and is inversely proportional to the square of distance r between P and the element. Okay, so we take the book away. Okay, so what have the parameter discussed? Okay, what is the parameter discussed? Later on we will see. Okay, before we proceed, you can see this is static field. Okay, so our sources here is moving charges. Okay, moving charges. However, you see J, okay, J equals to rho v, okay, rho v u. Okay, this one will be your constant speed. Okay, u is a constant speed. So you can see the equation. Where is the related equation here? J equals to okay, this equation is actually, you can get it from the previous subchapter, the previous chapter. Okay, J equals rho vu, you can see from the previous lecture. Okay, I don't know why they don't include here. Okay, never mind that. Okay, so there is three types of current sources. Okay, if in magnetic electrostatic field, we are concerned about the charges, line charge, surface charge, and also what, volume charge. Okay, however, it's different in magnetic field. Okay, we actually concerned about the current. Okay, about the current. Okay, okay, of course this is a vector. Okay, okay, so what we concern of three parts. Okay, three natures. Okay, which is current, line current, okay, or we can call it filament current, you can call it whatever. Okay, filamentary current. Okay, but just it's actually line. The next is your surface current, and this last one is your volume current. Okay, so what happened is that, okay, you can see this equation just now. You can see it's actually DH is proportional to your I dl over sine phi alpha over r square. Okay, so let's we discuss about this. Okay, so this one we can use the example for the line current first, the filament current. Okay, so let's say I just take example from the book. Okay, so you may refer to the book for more detailed explanation. So let's say you have a current here. Okay, you have a current of I. Okay, and you take a small sample. Okay, if this is your eye, okay, then you need to take a sample of DL. Okay, you have a long line and you take a small sample of DL. Okay, and DL is it can be in direction later on. Okay, this one is direct. You have it's a vector unit. Never mind. And then you want to take a sample. Okay, sample here. Okay, and here in magnetostatic field, you need to be aware of these two symbols. Okay, like this and like this. I think you learn this in your physics as well, secondary, or maybe in your electric subject. So what does it mean by this? Okay, this means that it is going inside the paper. You see, so this is your screw, right? Okay, just the same plus shape. So this one you take the same, so it is going in. Okay, going in. How about the next one? Is actually when you see from this view, it's just like a dot, right? So it's going out. Okay, going out. This one is going in. Okay, so this one is going inside the paper, this one is going outside the paper. So you need to be aware, okay, because this is with regard to the direction. Okay, so for this direction, it is here. Okay, okay. Okay, so now let's say we want to take sample. Okay, from here, this is our point of sample. So we have take this the same as we do in the electrostatic. We take a vector, okay, unit vector. Okay, then you have this as your direction. Okay, direction going towards here. Okay, sampling. So then what angle created from here to here is your alpha. Okay, so this is your DL. Okay, DL can be here and a lot of here. Okay, DL. So let's say you want to take here because our sample is around here, so you take DL. Okay, then what else you know? Okay, this is point P. Okay, point P. Okay, I just use the same so you guys won't get confused with the study book. Okay, so it is mentioned that DH, okay, is proportional to I DL sine alpha over R square. Okay, then you know when you want to make equations, you need to introduce constant. Okay, so you need to introduce constant. Okay, okay, then so this K is equals to 1 over 4 pi. Okay, so we finish about that. Then we expand it. Okay, if you want to include 1 over 4 pi. Okay, oh, certainly I is 1, so just write it accordingly. Okay, then when we want to see a cross product, okay, you remember cross product, what is the difference with the scalar? Scalar will use cos, okay, whereas cross will be using sine. Okay, so from the definition of cross product that you learned from the previous equation 1.1, okay, so it is better to put in vector form. Okay, because you see there is vector, right? This is in vector form. Okay, your I is vector, DL is vector, your R is also vector because it's moving, there is a direction there. So if you want to introduce vector, okay, introduce vector, okay, then you have your I DL, okay, I DL, and cross, okay, cross, because it's sine, okay, cross AR is the unit vector in R direction. Okay, the unit vector here, the unit vector means what magnitude only 1, and then 4 pi r square. Okay, so we know r is actually the the distance. Okay, distance between them. Okay, so of course if you want to expand it, okay, if you want to expand it to, you can have also this form, which is, okay, the distance, and also 4 pi r cube. So you know why is this, right? Okay, because this is from here. Okay, this is unit vector, this one is just a vector. Okay, a vector, but this one is a unit vector. Okay, different there. So and then in order to for you to know the direction, okay, in order for you to know the directions, you can use right hand rule or right-handed screw rule. Okay, if you have like this, okay, your field is in like this. Okay, if you say this is the line and this is your field circulating, so like this. So what is your direction of current here? Okay, your direction of current is going up. Okay, is here circulating your magnetic field, and also so it's here. Okay, this one is the same. Okay, or maybe other ways that you can see later on. Okay, how you actually determines the cross, because cross you need to know when we want to use cross. Okay, when we want to use cross, things that is parallel will result in 0, and things that are orthogonal will produce another direction because it's cross. Okay, sorry. For example, if you want to see the cross product, okay, in cylindrical coordinates, which involve the r, the z, and the phi, right? Okay, if you we want to see r cross of z. Okay, so what is the result of the cross product? Is the phi direction. Okay, so please be aware of this. Okay, so we finish with that. Okay, for example, and then you see there is a line current, surface current, volume current. So what is changing in terms of the units? Yes, it's according to the nature. If your line, you have meter. If you have surface current, you have meter square. And if you have a volume current, you will have meter cube. Okay, so for the line current, you will have your IDL. Okay, the unit for this is ampere because current, ampere meter. How about surface current? Surface current, you will have I meter also. Okay, later I show you guys why it is like this. Okay, and second, volume current, you also have AM. Okay, now let we see from this equation, the one that we have here. Okay, okay, so for the IDL, okay, IDL you have AM. Okay, there is no issue about this. How about the surface current? Okay, the surface current, you want to see for JS ds. Okay, means with respect to the surface current. Okay, with the respect to the surface current. So if your J, okay, if your J is what? Is A per meter, okay, and your ds, okay, and your ds is meter square, so this one cancel out, then you will have AM. Okay, the representation of the surface current is that you have a surface, then you have a small sampling area. Okay, then you have your JS. Okay, and also you are able to obtain, okay, the nature of this. Okay, the next one is what? The next one is, let's say you can have a cylindrical. This is volume. Okay, volume means your surface, your cross section will be here. Okay, flow. Okay, so for the J of dV, okay, this one is JSTS. Okay, so J is what? J is A per meter square. Okay, why is meter square? Because we are considering this surface area. So this is your J. Okay, so then what is your dV? dV is volume, right? Meter cube. So that's why you have A M. Okay, so whatever nature of line current, surface current, volume current, you have a meter. Okay, so okay, so this one is what I already explained just now. Okay, now we go to the equation involving the line current, surface current, and volume current. Okay, so as we already saw just now, okay, our line current, this, where is, okay, this is our line current. Okay, so let me rewrite again. For the line current, we have H, electric field intensity, and magnetic field intensity, and what, single integral, because it's line only, vector dl, and also unit vector in r direction. Okay, and you have 4 pi r square. Okay, this is just a distance. Okay, this one is a unit vector, where you know unit vector is what. I just hope that you guys don't confuse. Okay, okay, can you see now? That's why if we expand it, this one will become r cube. Okay, then the next is surface current. Surface current, you have H, but now it's double integral now because it's your S. Okay, then we have introduction of K. Okay, we have introduction of K. Let me put different colors so we can see the difference. Okay, later I will explain more. K, okay, then we have ds because it's a surface, and cross. Okay, cross with our AR over 4 pi r square. Okay, next is volume. What you have is a triple integral, right? Because it's volume. Then you have your J, okay, D volume, cross of A, the same thing, 4 pi r square. Okay, so if you notice the difference between this and electrostatic field, electrostatic have permittivity. Here we don't have permittivity. Okay, it's a bit similar, it's similar but not the same. Okay, so we don't have permittivity here. Okay, so why we have this K and J? Okay, okay, is explained just we can have different charges. See figure 4.1. Okay, you can see figure 4.1. Okay, so this is different, right? Type of charges: point, line, surface, volume charge for electrostatic. Just as we can have different charge configuration, we can have different current distribution. Yes, correct. Just now, line current, surface current, and volume current is shown in figure 7.4. Okay, so this is your line current, this is your surface current, this is your volume current. Okay, as shown in figure 7.4. If we define K, okay, if we define K as the surface current density in ampere per meter, and J as the volume current density in ampere meter squared, the source element are related as. Okay, so remember, if they say K is surface current density in ampere per meter, and this one is ampere per meter squared. Okay, so this one we can relate actually. IDL is actually analogous to K ds, sorry, K ds and also your J dV. Okay, so if we take into account that this one is measured in is current density, right? This one is current density, this is volume current density, so this is in ampere per meter, and this one in ampere per meter squared. You know, right, why this ampere per meter squared just now I show you guys. Okay, so you see the equations, okay, how they actually saw that. Okay, so J, okay, is the surface, is the volume current density, okay, volume current density times with your differential of volume. How about K? K is your surface current density, okay, in ampere per meter, surface current density. So, okay, then you see this guy, just like I show you guys why we can have R power of 3. This is the same as like coulombs, okay. Okay, actually they expand this. That's why we have, instead of square, we have power of 3, okay, because this one times this one is power of 3. Okay, we can go to this okay, in electrostatic field, okay, that I ask you guys to watch the video, okay, because he's explained just the same thing about finite and infinite line charge, right? So in magnetic field, we also have things like this, almost similar, a bit similar. We can use almost the same concept to get our experience H field, okay, at the point of sampling. Okay. So okay, I want to see the slides. Okay, you guys can refer the slide also, okay, because the slide, I'm sure there is more information, okay, and good for you, okay, to have more reading and in many things, okay, and of course try the exercise. So okay, we may take some time to do this derivation because I didn't do it last time, so but you have watched the video, right? So let's say we have axis, okay, you take this xy and z, okay, then you have a line current, okay, you have a line current, for example here, okay, I just put in yellow color, okay, your line current. Then you have the sampling point, okay, sampling point can be everywhere. Let's say you want to here, so easy understanding, okay. So if you see, this is in 3D, but if it's 2D, we need to show whether it is inside the patch, going inside or going out, okay, just like the situation just now for the screw, okay. So this one is 3D, so it's okay. Now so you have this as your line charge, line current. So then you create a vector, you create a distance now, okay, with this, okay, just like the same. So you create, okay, with 90 degree with respect to the axis, okay. So far so good, okay. And you have the length, okay, can be from point A to point B, okay. And you can have sampling point at any of these length along the line, okay. You can have it here, you can have it here, you can have here, okay. So then you need to take the differential of the z here, okay, differential changes in z direction, okay, and then this is your sampling point, so this is your R, okay. Okay, so what we know from our Biot-Savart's law is that we have dH. Do you guys see this? Because I'm now sitting down, okay. dH equals to I dl, okay, cross, okay. Remember we are using cross, okay. cross AR over 4 pi R square. Okay, so using Biot-Savart's law, okay, using our Biot-Savart's law, so you know that dH, okay, for the line charge, okay, dH is equals to I dl. Okay, this is the general, and this one is more specific. Okay, so you have when you have this, we also need to show the direction of current. Okay, that this is going up. Okay, your current direction. So if later on, if your Z is going down, so it is negative. Okay, because it's opposite the direction of your current. Okay, so if you have your I dl, okay, I dl, now you can see the changes. What is the changes in L vector? Okay, in L vector related of this is actually changes in Z direction. Okay, in Z direction. So let's say this is your the units. Okay, the differential of your dz. Okay, then you have your I dl is actually I. Okay, the same I, and also however this dz. Okay, the movement in dz, and also in the vector unit. Okay, z. Okay, now if you want to determine the r, okay, r, you see r is here, right? So it's actually going here. If you want to see the combination, okay, it's actually going here and going towards here. Am I correct? Okay, so it's actually r, okay, r and r unit vector. Oh, okay, I'm sorry, I missed one step that is very important to you guys, because you know, sometimes we assume students understand. So this one we try to model using what? Is it Cartesian, spherical, or cylindrical? Because it's r, z, and phi, so it's cylindrical. Okay, cylindrical. So then you have this. Okay, now you obtain this. But how this one? This one is actually, because it's opposite direction, so it's negative. Okay, then you have z minus of your z. Okay, z direction. Okay, so then what is your dh? Okay, your dh is actually I dl here. Okay, cross product of r minus okay, over 4 pi r square. So what is your r just now? R is this. Okay, I don't want to make it a bit it will be like a bit complicated. Okay, but never mind. Okay, so we try to use this one. Okay, which is the power of 3. Okay, this one is power 2. We just expand our unit vector, so we will have r square for the magnitude. Okay, plus z1 minus z. Okay, square of 3 over 2. Okay, so if you guys notice, this and this are parallel. In vector, in cross product, the parallel will be 0. So this one 0. Okay, now we left this and this. So okay, if you see, this is z going up and r going here. Okay, r going here. So z r, okay, z r, z here, and r, so you have here. So what is the changes? Is in phi direction. Okay, or you can use this this simple notation. If you have z, you have r, you have phi. Okay, so if you have z to r, then the next one is your phi. Okay, so you do this one will result in phi. Okay, direction. Okay, we do some, I just skip. Okay, so that we can go it very fast, because I want to go to the tutorial. Okay, 4 pi r. Okay, then we will, but what we have after that, we have b over z. Okay, when we want to do the integral, because this involve the line, okay, so what integration is that you have is actually from what, from a to b. Okay, am I correct? From a to b. So your b minus z over r square plus b minus z square minus a over z, okay, over r square a minus z. Okay, okay, so what is the unit? Ampere per meter. Okay, for your h. Please be careful about the unit. Okay, okay, so then we applying integral identity. Okay, this is provided inshallah, because we engineers, we only use, we don't need to memorize. Okay, so question 295. Okay, 295. So they show this integral identity. Okay, so we can use directly. Okay, then what? Okay, but before we want to relate, just like electrostatic, okay, we want to relate this with your sine alpha, with alpha, right? Okay, the same also for here, this case. Okay, so we can go for the 2D. Okay, 2D. So in 2D, that's why I told just now, in 2D we need to have direction going inside or going out. Okay, and for our case it is going inside. Okay, so this is your sampling point. Okay, this is your sorry for the bad drawing. Okay, this is your alpha 1, this is your alpha 2, this is the directions. Okay, h is into the page because screw going in, and then after that again, then you have what, differential. Okay, let's say there is a differential here that you want to take. Okay, so then you have your z here, and you have your b here, and you have your a here. Okay, so this is your point A to point B. Okay, C is the different. Okay, this is capital A, capital B, this is small b, small a. Okay, so you can see, if you want to see the relation, okay, the relation between them. Okay, so taking this is, let's say, your P. Okay, you can use R also, is okay. Okay, but as long we know what is this. Okay, so what is sine? Sine is actually what is sine? Sine is actually this one, opposite type over hypotenuse. So for sine 1, alpha 1, okay, the opposite, which is your B, okay, which is your B minus Z. Okay, sorry for the confusion. Okay, remember that I told you guys, oh, this must be because of the night time, I feel really tired. So you see, like just like I mentioned in the video last time, alpha 1 is actually the point minimum. Okay, so this is your point minimum, this is your point maximum. Okay, so this one terbalik, sorry, I label it terbalik. So that's why I'm a bit blur just now. Okay, so if you want to take alpha 2, okay, alpha 2, okay, sine alpha 2, what is that? Is that you have b minus z, okay, opposite, then you have your hypotenuse. So what is your hypotenuse? This is actually your hypotenuse. Okay, and of course square root, okay, because it's a dimension, because it's a length, okay, it's a magnitude. Then how about sine alpha 1? Alpha 1 is actually from here over here, okay, the opposite over this hypotenuse. So what is that? Is z minus your a, okay, z minus your a. So don't really care about this difference, okay. You can have a minus z, z negative a plus z, that still mean the same thing. And then you have the hypotenuse, okay. What is the hypotenuse? R square plus a minus z square, okay. So here you can see, right, we try to make it look nice, okay. We pull out the negative out, okay. So you can pull out the negative out also. It's still the same thing, okay. So from this lengthy equation, okay, from this lengthy equation, so you will have h equals to I over 4 pi r, okay. Then you replace it with sine alpha 2 plus sine alpha 1, okay. And what is the, because we have direction, right, so this just now, this one z cross r will result in phi, okay. So you have your phi now. So this is the equation, the simplified equation for this long version, lengthy versions, okay. So you can find h at anywhere for the line chart, for the line current using this. So I don't want to waste time, okay, it's already 42 minutes. So let's we go for the tutorial question, okay. So tutorial question, I just go to the simplest one, okay, because it's to help your understanding, okay. So so now it's 2:53 a.m. okay. I really hope that I don't fall sick because of things like this, okay. So find magnetic field intensity H at 1P002 and 2Q020 for the circuit carrying current as shown in figure below. So this is your circuit carrying current, okay, and you can see the direction, okay. I don't want to solve for all cases, so I just want to let's discuss, okay. Discuss means I will not provide the exact equation, I mean from A to Z, just for you to have your understanding. So we discuss about 002, okay, at point 002, okay. So okay, we put this away. If this is page 1, this is page 3 then, okay. Now we go for tutorial, okay. Tutorial, you have this tutorial, so okay, you can try to do it, okay. Tutorial 7, okay, find the magnetic field intensity. So we want to find the electric field and magnetic field intensity. So you can see this is the view, okay. So just for us to really see it very fast, okay, you can see this is 0, 1, right. So you can know is what is your magnetic here, because it's hypotenuse, right, 2 1 plus 1, so this one is actually your Z2, okay. Directly you try to do the mathematical, so this one is also Z2, okay. Okay, so what you can see, so from this view, from this point, okay, if we observe, okay, the H field, okay, you can see, right, this is your point of observation. H is 0 because it is symmetrical, okay. H is 0 because it is symmetrical. So what does it mean by that, okay? So you can see H just now is actually in H equals to, oh sorry, sorry for that. Okay, you see H is actually IDA, right? So it's with respect to the direction. Okay, so you can see it is symmetrical because you can see it uniform, just nicely symmetrical divide by, you see the same directions and opposite direction. Okay, that's why it's 0. Okay, wait for a while. Okay, so you can see because of symmetrical nature, so the electric field intensity looking from point here is actually 0. For example, if you want to see your electric field intensity going from B to A, okay, going from B to A is actually is opposite of H going to BC. Okay, okay, then how about this one? How about the next one? We try to see, okay, we try to see in terms of the horizontal, okay, this one. And how about the next one? Horizontal component, so you have DE, right? H DE is actually in the opposite direction. You see this one? Okay, D to E, F to E, B to A, B to C. Okay, then what else you can see? Okay, yes, the vertical component now. The vertical component, A to F equals to, you see, A to F and C to D. Okay, okay, so then what happened? We already covered this, we covered this, we covered this, covered this, covered this. Now we have this, we cover this. Okay, you can see this one, HAB is actually the resultants. Okay, so since they are in equal like symmetrical, so the resultant here, which is your HEB, okay, is actually equals to 0. Okay, now we want to solve this question using the simplified equation that we have obtained. Okay, which is H equals to I over 4 pi r sine alpha 2 plus sine alpha 1. Okay, okay, we want to solve using this equation. Now we want to solve for HBA. Okay, HBA. Okay, so what we have, I over 4 pi r. Okay, so we take out this. Okay, HBA, so you have set to 1 1, right? Okay, so this is your alpha 2. Okay, so so your sine, what is your alpha? Anyone can guess? Alpha 2. Okay, alpha 2 is actually okay, so sine alpha 2. So this is your alpha 2, right? So alpha 2, this is your I. Okay, this is the point, which is your A, B. Okay, and this is the sampling point. Okay, this is the coordinate. So this is the direction of the current. Okay, of the current. So I'm not sure where why this question didn't provide us with current. Oh, okay, there is current. Sorry, I didn't really look at this. So there is current, you see. Okay, sorry, I really okay, this one is your 5. Okay, so this one is what? This is your R. R is actually the distance, okay, from the point sampling to this, okay, which is actually your 1. Okay, then you have sine alpha 1 alpha 2 plus sine alpha 1. Okay, then you should know this one is actually the result of cross product, right? Cross product. So we need to see this cross product also. What is our cross product here? You can see this one is actually this one is actually y and z. Okay, see they've given this hint. Okay, so if y cross z, you will have x. Okay, orthogonal. Okay, just like this. Okay, x y sorry, y z, then you have your x. Okay, okay, so we substitute. Okay, I over 5 over 4 pi and 1. Okay, so what is your sine alpha 2? Okay, what is your sine alpha 2? Anybody? Okay, so this is 1, this is 1, sine alpha 2. Sine alpha 2 is equals to what? This one over this one. Am I correct? Okay, am I correct? This one over this one. So where's the calculator? Because I know it's simple, just you want to show through calculator. Okay, to show you actually instead of just directly use the answer. Okay, where is the calculator? Okay, so 1 divided by square root of 2. Okay, then you have your sine, inverse sine. Okay, so alpha 2, sorry, sine alpha 2, this one 1 over this one. Okay, sorry, this one is just, we don't need to know the I'm sorry, I'm mistaken. This one doesn't need to know the angle. Oh my god, I am very sorry, due to night time I'm very tired. So sin alpha 2 is actually the ratio, right? So you can just use the ratio. Okay, I'm sorry, I am so sorry. Okay, then what is your alpha 1? Okay, so your alpha 1 is 0. Okay, you don't have alpha 1. Okay, so this one is the result of y cross z. Okay, that's why you have x direction. I am so sorry. Okay, just to make you confused. Okay, then you have 1 over this one. Okay, then what is your HBC and what is your HBA? I am so sorry. Okay, so 4 pi times 2, then 5 divided by answer, so you have 0.2813. okay, in x direction. So since then you see the HBA is actually in the opposite direction of HBC. So once you know HBA, you can know HBC. Okay, sorry, which is the negative of HBA. Okay, so based from this, okay, based from this, you can settle the rest. Okay, you can settle the rest for your DE. Okay, you can settle the rest for what else that DE and also your AF. Okay, So for DE, you can try yourself. Okay, instead of you can lengthen the this triangle. Okay, because it's here, DE is here. Okay, you can lengthen them. So I just provide you some. You can do it later at your own convenience. You have your DE. Okay, this is your sampling point. Okay, now what is your here is 1, 2 and 3. Okay, so you have this as your 3 unit, and then this one is your 1 unit. Okay, so you know what is your magnitude, right? So it's which is 10. Okay, so the same thing, you can try this. Okay, hash DE I over 4 pi r. Okay, then you can use, okay, you just use the same. Okay, replace accordingly. I'm sorry, oh my god, I must be too sleepy. Okay, so you see this one, the tutorial 7. Okay, okay, so this is for line current. Okay, of course the challenging that we have many types of other current, which is surface current, volume current. Okay, so thank you, you guys. Okay, you can try this at your own convenience tutorial. Okay, so this one, circular disc with radius b centered at origin. Okay, so if there is radius, if there is a surface current, let's say J, okay, on the surface of the disc, determine the magnetic flux B at point ZB. So I think for this equation, okay, I just provide some visualize to you. Okay, so for these two, okay, centered at origin. Okay, okay, centered at origin, you have cylindrical disc. Okay, like this, and it says with radius B. Okay, so this is your radius B. Okay, if there is surface current density on the surface of the disc, what this is here, okay, this is your JS, because of 16R phi on the surface. Determine the magnetic flux intensity at a point Z equals to B. Okay, Z equals to B, let's say here. So we want to find the B. Okay, so I think this one is the same for the force, the Coulomb force you also learn, right? So you have you will have something like this. Okay, okay, then later on you diverge the components. Okay, you diverge the components. You can see this one is going here. Okay, and this one is going out. Okay, you can see it's different direction, right? The current direction. Then actually, if you want to see from the angle 2D, you will have X and Z. Okay, then you have, let's say here is your point here. Okay, then you have like this. Okay, then you have vector direction. Okay, so you need to split it into the horizontal and vertical, and later on there will be some cancel out. Okay, cancel out, because like this and this, they can cancel out from one another. This one is due to the next point, which is here. Okay, okay, so this one will be cancelled out the horizontal, then we will take the vertical components. Okay, for our resultants of B. Okay, so the B unit is here, B per meter square. Okay, WB per meter square. So okay, thank you very much everyone. I am so sorry for a lot of mistake here and there. Okay, thank you so much, and see you guys in the next lecture. Assalamualaikum warahmatullahi wabarakatuh.